Okay, this week we're moving on to where the energy for the Earth comes from. That's the sun. The sun is the driving energy for all of the atmosphere's motion. So we're going to learn a little about how that energy arrives and how it's distributed through the atmosphere this week. Radiation and understanding it is not one of the simpler subjects in meteorology, but we're just going to touch at the surface. There are some equations shown to you this week, but we're not asking you to learn how to use them fully or anything like that. You'll just have a general idea of what they mean. So let's see if we can get into this a little bit here right now. So how does the energy flow into and out of the Earth? Oh yeah, all that energy that comes to the Earth, we have to be able to maintain no more than that energy. So what energy arrives from the sun also goes out from the Earth, so that there's a balance here. So we have an electromagnetic spectrum, or radiation. You look outside and you see light. You can see things with your eyes. Those are electromagnetic waves. X-rays are electromagnetic rays. So there are different varieties of them. And here you can see a table with what they look like and where the collars are, most of them. And they're in the ultraviolet radiation spectrum, and that is radiation that actually is coming from the sun into the air. And we talk about these are wavelengths. They are waves. So I think about them like an ocean wave. The wave comes and breaks on you, hits you, then you go down into a trough where there's not much water, and then it comes back to the next one. And radiation waves are just very similar to that. One key point of electromagnetic radiation is it moves at the speed of light. All of it does. So when there are a whole bunch of very short wavelengths, there's a lot of energy coming by your point at one moment in time. When the wavelengths are pretty far apart, there's not as much energy coming by. So with electromagnetic waves, if the wavelengths are very short, they're very powerful, they have a lot of energy. If they're very much longer, they have less energy. So a black body. The Earth and you, for example, are considered black bodies in that when you absorb temperatures, you also radiate the same amount of radiation back out when you get the input. So the Earth has maintained a relatively constant temperature. It doesn't vary a lot. So that means that it is a black body in the sense that it absorbs the radiation coming from the sun, processes it, uses it, and re-emits literally the same approximate amount to keep that temperature. So that in essence is it's not a perfect emitter. It's not a perfect black body, but it's very close. But when you have a black body, the mathematical laws become much simpler. So we're going to assume both the Earth and the sun are black bodies for this course. So Wind's law is just that the maximum wavelength of the most intense radiation is proportional to the absolute temperature. So the higher the temperature, the shorter the wavelength. So that means if you have the sun's temperature, which is way hotter than the Earth, the wavelengths are going to be very short. If you have the Earth's temperature, the wavelengths are going to be longer. And here's another one. The power of the energy, temperature to the fourth power is proportional to the energy coming out of a black body. Well, guess what? The sun is a whole lot warmer than we are, and if you multiply it times each other, that temperature 4 times, think about how much bigger that number is than you're multiplying the temperature of the Earth the same way. So sun has a whole lot more energy than we do. Now, as you move away from the sun, less and less of the sun's energy gets to you. So, and it's simple enough. The equation is 1 over the distance from the sun, radius from the sun squared. So if we're at 2 times out, then you multiply 2 for the radius and you square it, you get 4. So the energy would be 1/4 the amount. So in other words, if the Earth was moved twice as far from the sun, we would only have 1/4 of the energy, not a half, but 1/4. So if it moved out even more, think about how much that would decrease. That's why as you go out in the solar system, the amount of energy reaching these planets are getting less and less. Another part, the sun is directly overhead, somewhere between the Tropic of Cancer, the Tropic of Capricorn, or the equator at all times of the year. It's moving because our Earth is tilted. Well, if you ever look at a flashlight, if you have a flashlight pointing straight down, you get a very concentrated beam of light. Well, if you have a flashlight pointed at an angle, your beam spreads over a larger area and it's not as bright. So think about the sun pointing directly down over that area, the equator. You have a very concentrated beam. A lot more energy is arriving in that part of the Earth than is arriving up at the North Pole, where the angle of that sunshine is much different. So that means that there's more energy coming in by the equator than there is by the poles. So the energy, all this energy from the sun is not distributed nice and simply all the same everywhere on the Earth. It's changing. It's becoming the most following where the sun is directly overhead. So say right now where the sun is more in the southern hemisphere, most of the energy is going to the southern hemisphere. Less is coming up north. That's why we're cold. And here you can see that the angle incidence from the sun is 90 degrees perpendicular right into the Earth, right here at the equator at an equinox. So on March and in September, we have an equinox. At that point in time, the top of this Earth, for the first time, begins to get a little bit of sunlight back. So think about it. If the sun is in the southern hemisphere, the North Pole in that area up there is not getting any sunshine. It's no wonder it's getting pretty cold up there. And here you can see the amount of solar radiation coming in different areas, depending on the sun angle. One of the interesting things, here's Brockport, New York, which is Long Island area. And you'll notice that in the wintertime, not a lot of solar energy coming in there. But it picks up pretty quickly. And notice how much more is during the summertime. And then goes back down again. But Singapore, which is down near the equator, has pretty much normal amount of average, very close to the same amount of solar radiation. So in the summertime, we're actually getting a decent amount of solar radiation in the northern hemisphere. And that's why we warm up so well. And here you can see why that is. Notice the tilt. The tilt never changes on the Earth. So when the Earth's orbit around the sun is this location, it's summer solstice, that tilt is facing right towards the sun on the northern hemisphere. In the wintertime, on the other end of the orbit, the southern hemisphere gets the tilt. So it's all because of that tilting, the 23.5 degrees the Earth tilts. So what happens to all this radiation that's coming to the Earth? Well, some of it gets scattered, some of it gets absorbed, some of it gets reflected, and some of it's transmitted back out from the Earth as a black body. But that's got to all equal 100% of the amount of radiation that we got. So scattering, it's why we see blue in the sky at night, in the daytime. Is me scattering, it's called. But another thing is, think about it with a cloud. A radiation hits the cloud, it's going to scatter in all different directions. Hits a raindrop, it scatters. You see a rainbow. So there's some radiation moving in all different directions when that happens. Some of it is still coming into the Earth. Some of it may be going back out to space. And reflection. I have a snow cover today at my house. Rare moment in time. But if the sun comes out later today, it's going to reflect a lot of that sunshine back. And you look outside when it's bright, fresh snow, and you really need sunglasses because it's so bright, the snow. All that reflection of the solar energy. And that means that's all being reflected back into space. So when there's snow on the ground, you have less energy reaching you and staying in your air. Most of it's being reflected back out into space because the snow is so white and highly reflected. It's an albedo. And then part of it is absorbed. Part of it's absorbed by chemicals. Ultraviolet radiation is absorbed a lot in the ozone, in our stratosphere. Other parts of the atmosphere absorb different radiations. And the ground absorbs solar radiation. That's what warms the ground. And here is just an example of that albedo and that snow. So here is what we call the planetary albedo. So roughly 30% of the Earth's atmosphere system is reflected back into space. Another 23% is absorbed by the atmosphere, and another 47% is absorbed by the Earth. And if you do the numbers, that works out to keep the temperatures of the Earth about the same as a black body would. And here you can see where the different layers kind of pick up on some of the solar energy coming in. But there must be equilibrium within our system. So the Earth, because it's not as hot, transmits most of its radiation in infrared. And as part of that, we have gases in the atmosphere called greenhouse gases. They include such things as carbon dioxide, which everybody in the world talks about, but they also include water vapor. Water vapor is actually the principal greenhouse gas in most of the atmosphere. Greenhouse gases absorb infrared radiation, so the ultraviolet radiation that comes in from the sun passes right through them, but when it comes back from the Earth as infrared radiation, it gets absorbed. And then that gets projected back towards Earth and back towards the sun. So part of the extra warmth our Earth has is due to greenhouse gases. So, and the principal one, like I say, is water vapor. So let's think about water vapor. If you live in a very moist climate, we'll say along the Gulf Coast or in Florida, you have all this sunshine that comes in, and at nighttime, sun's gone, right? You would expect infrared radiation from the Earth to be pretty high at that point and just going back out into space. Well, if you look at the Gulf Coast or Florida, when it's very moist and humid, what you find is temperatures drop some at night, but they don't drop real far. Now, go to the desert, completely dry climate. What happens? All that sun's energy that comes in gets reflected back out as infrared radiation, sent back out in the nighttime, and those temperatures drop like a rock. They go way lower. So that's why you can see the impact that water vapor has on all this, keeping us greenhouse and warmer. The final part here is the calendar effect, where they talk about the carbon dioxide has been increasing faster and faster each year. And one of the interesting things is, though, think about it, when the plants are out, they absorb carbon dioxide. So you actually get a decrease in carbon dioxide in the atmosphere when there's a whole bunch of plants growing. When the plants are not growing in the wintertime, carbon dioxide goes back up. And so you can actually see that in the Keeling curve. So now the last thing I just wanted to talk to you about here with all this, I just wanted to show you really on satellite how we can look at different bands of radiation. We talked about them here, and we have, like, right here is just a reflected color image that is just every band of light coming out from the Earth. We can see that in this image, and if I do an animation of this image, I can actually see what I would see if I was in a spaceship looking up to the sky. One of the interesting things right now is look at all this snow cover. This is all snow cover right here. Here's a big low, but you can see how bright the clouds are. See how bright the snow cover is. That's the albedo being very high. Now, look out here, not so high. So that's just one aspect of this. But if I wanted to go to another curve, And there are whole bunches of this infrared radiation here. We can look at water vapor. We can look at different cloud types. We can see dust in the atmosphere here. We can see different blue visible. We're looking towards the blue light here, or here's going to red light. Here's the vegetation, more infrared coming from that. We can see high clouds, high moisture, more of the snow reflecting. And down here you can see upper level water vapor. All of these transmitting at different bands. Not a lot of difference in band length or whatever, but each one of these has a particular area in the atmosphere they transmit from. And if you understand it and utilize it as far as looking at satellite image, you can get a tremendous, tremendous amount of information about the atmosphere that way. So I just wanted to give you that today. Hope you enjoy this section. Please don't hesitate to ask if you have any questions.